All right, so at the beginning of Chapter 4, we're going to talk about different properties of solutions. So Chapter 4 is called Reactions in Aqueous Solution. So first of all, we're going to talk about properties of solutions. Then we're going to talk about the three primary reactions that we have that occur in aqueous, meaning dissolved in water solutions. So we'll talk about precipitation reactions, acid-base neutralization reactions, and then oxidation reduction or redox reactions. And then we'll quantify that by learning about a little bit about how to calculate concentration units. We'll just do the most common concentration units and leave the more complex ones for next semester. And then the last section of Chapter 4, we'll put the reactions and the quantitative part together and learn how to calculate values associated with a reaction in aqueous solution, such as what is the concentration of an unknown acid in an acid-base titration, or how much precipitant was formed. So first of all, electrolytes versus non-electrolytes. This is a way of classifying solutions. So we've all heard the term electrolyte. Where do we always hear it thrown around in? Gatorade, right? Classic. Gatorade made electrolytes just famous, right? What are electrolytes?
Sodium and potassium.
Those are examples of electrolytes. Sodium and potassium ions are examples. But what are they? They're ions. Good. They're ions dissolved in water. So very important for us when we are, say, working out and exerting and we are sweating. When we sweat, we lose both water and some electrolytes, because when we sweat, we're releasing salt as well as water. But if you're working out a lot, say you're running a marathon and it's 100-degree heat and you're sweating a whole lot and you just keep on replenishing with pure water, then that pure water is not going to have the same concentration as ions as your bloodstream, and that can cause a lot of problems, including water toxicity. What can happen if you get water toxicity? Do you know? Your cells could explode, right? Yes. How well does that turn out for you? Multiple organ failure, it can kill you within hours, yes. So once in a while you see on the news that somebody running in a marathon collapses and it has water toxicity, and sometimes they don't make it. But that's why drinking those electrolyte solutions is important if you are in that kind of situation. Now, if you're the kind of person who just goes to the gym and runs on a treadmill for 20 minutes and gets off, yeah, water is fine. Gatorade is mostly sugar in the end of the day. It's a marketing ploy. But if you are a professional athlete or you are running out in the heat for hours on end, then yes, that's a good idea. So let's talk about what makes solutions electrolytes. We already said that they contain ions. So a solution is a substance that when dissolved in water yields ions. And the importance of those ions is those ions enable it to conduct electricity. Whereas non-electrolyte solutions are ones that when dissolved in water do not produce ions and therefore cannot conduct electricity. So up here I've got two different common soluble household substances, C12H, come on, where's my dot? Come on, I need a dot, the laser pointer, sure. C12H22O11, anybody know what that's the chemical formula for? Give you a hint. C6H, 6OH. Okay, sorry. Like I said, most of it was 6. It's sugar, right? So this is a disaccharide. So glucose is a monosaccharide. This is a disaccharide. So it's a glucose and a fructose stuck together, aka sucrose. So this is sucrose. So we're table sugar. Does it dissolve in water? Yes, good news for all of our Southerners who love sweet tea, right? It does dissolve in water. When it dissolves in water, all that changes is its state of matter. It goes from a solid to aqueous when it dissolves in water. That is all that happens. It is a molecular compound. It does not contain ions. Whereas here's NaCl. Now, I know you guys know what that is. What is that? I've heard of it. Salt. Good. That's table salt. Does that dissolve in water? Yes, that dissolves in water, right? But when the salt, which is an ionic compound compared to sucrose here, which is molecular, dissolves in water, it breaks apart and we end up not with sodium chloride units floating around the water, but with sodium positive ions floating around and chloride positive ions. This is called dissociation, when it breaks apart. These ions in the water therefore allow the water to conduct electricity. So We can also get ions from molecular compounds through a second process called ionization. So dissociation is how an ionic compound breaks apart. Ionization is how a molecular compound, in some special cases, can break apart and cause ions. So here is hydrogen chloride, which is molecular. There's no metal, there's no ammonium, it's definitely molecular. But when we put it in water, we got ions here. So what is special about hydrogen chloride in water? What does it turn into? Hydrochloric acid, which is an acid. So ionization happens with acids and molecular bases can ionize. And so this is the second way we can get electrolytes. So we can get electrolytes by ionic compounds dissolving in water, or we can get them from acids and bases dissolving in water. And these are the two different ways that we can get electrolytes. Bases, there's two different classes of bases. We'll cover that more when we get to acids and bases. But for now, let's look at molecular bases, or things that are molecules, not ionic, but are bases in water. The classic example of that is ammonia. Ammonia is NH3. So ammonia is a gas. When we dissolve it in water, it's not going to by itself break apart like the hydrogen chloride does. It's actually going to ionize the H2O molecule. So that means it's going to take the H2O and rip off one of the hydrogens and take it. Now when NH3 rips off a hydrogen plus and takes it, it becomes NH4. That is ammonium, a polyatomic ion. While H2O, when it loses one of its hydrogens and a positive charge, it becomes OH minus. That's also a polyatomic ion. What's that called? Hydroxide. Good. So we still got ions in solution, so ammonia would still be an electrolyte. So when we're identifying acids and bases, with acids, usually the clear indicator that it's an acid is that it starts with the all-important hydrogen. With bases, it's a little bit trickier. For the purposes of this chapter, to recognize a molecular base, I'm going to say it's an amine. Now, an amine, we learned about that briefly in Chapter 2 when we were naming compounds, is a functional group that occurs on molecular compounds that contains nitrogen and hydrogen, one or more hydrogens. So when I say amine, I mean it just has hydrogens, or nitrogen and hydrogen. So if it has nitrogen, hydrogen, I'm just going to put an X there, some number of hydrogens, this is an amine. And regardless of what starts on this side of the molecule, this is going to be a molecular base.
Does it only have one nitrogen?
No, it can have several. I mean, here we have 3.
No, nitrogen.
Oh, no, you can have more than one nitrogen group, but the amine group itself usually just has one nitrogen in the center. But you can have more than one amine on the molecule if it's a larger molecule. So the simple definition of an acid we're going to go with right now is an acid releases those hydrogen plus ions in solution, like hydrogen chloride did, and a base produces hydroxide ions in solution. When we get to acids and bases, we'll talk about a more precise definition we more commonly use, but this is called the Arrhenius definition, and it was the original definition of acids and bases. An acid produces hydrogen ions in solution, a base produces hydroxide ions in solution. All right. Electrolytes can further be categorized as either being strong electrolytes or weak electrolytes. A strong electrolyte is one that dissociates or ionizes completely. So close to 100% of what went in broke apart. Whereas a weak electrolyte is one that only partially. So what kinds of things are strong electrolytes? All water-soluble ionic compounds dissociate completely. So they're all going to be strong electrolytes. So sodium chloride, salt. It's water-soluble, it's ionic, it will be a strong electrolyte. What else is a strong electrolyte? Strong acids are strong electrolytes. So what's the difference between a strong acid and a weak acid? Well, the definition of electrolyte is the difference. A strong acid is one that ionizes completely, while a weak acid only ionizes a little bit. How do we know this? Look at this reaction. So here is our hydrogen chloride breaking apart, hydrochloric acid to hydrogen ions and chlorine. Notice the arrow just goes one way, just one way. If it goes just one way, that means the reaction goes completely over the product side. You end up completely with those ions. Whereas if the reaction went both ways, let's backtrack real quick here. Ammonia, notice the arrow went both ways. If this reaction goes both ways, that means at the end of the day, when the reaction kind of reaches its equilibrium, we're going to end up with a mixture of both reactants and products. So that means it did not ionize completely. So when you're looking at these reactions, if the arrows go both ways, it did not ionize completely. It is a weak electrolyte. Whereas if the arrow goes just one way, then it did ionize completely, and it's a strong electrolyte. So back to the idea of strong acids versus weak acids. If it has the hydrogen in front, and it's not just like water, yes, water has hydrogen in front, but it's not an acid, or hydrogen peroxide is the other example, H2O2, that has hydrogen usually written in front, but is not an acid. Yes?
Wouldn't this mean that if you had like a limiting reactant that you would have a weak electrolyte into a stronger one?
Well, if you're in aqueous solution, H2O is always going to be excess because you're always going to have a lot more water. So in this case, I mean, if you look at these, they're in water, but technically there's only one reactant. So you can't really have a limiting reactant.
So why are the arrows is there a reason that they're thicker and thinner in some areas?
Why the, yes, I'll get to that when we get to the very last one, the HSO4 minus, yeah.
So like water is present on like both sides?
Water's not technically a reactant here, it's just facilitating the ionization. So it's an aqueous solution, AQ, means it's in water. So it facilitates the reaction, but it's not technically a reactant here. In the next, or two more sections when we talk about acid bases, we can see how we can rewrite this with water as a reactant. But for now, we're just going to leave it off. So notice on this table, table 4.1, which is on your page 131, there are 7 strong acids listed: hydrochloric, hydrobromic, hydroiodic, nitric, chloric, perchloric, and sulfuric. Any other acid, therefore, will be weak acids. So if you're not one of the 7 strong, you're automatically a weak acid. That's how you tell if it's a weak acid or a strong acid, by referring to this table or memorizing the 7 strong ones. That's fine. Anything else, therefore, would be a weak acid. Now, one of these things is not like the others. Which of these acids looks different than the other ones? The bottom one, sulfuric acid. It also has a little asterisk there, which tells you something's going on differently here. So what's different about sulfuric acid compared to all these other acids? What's different about him? It's weird. Look at the hydrogens. What's different about its hydrogens? Has 2, right? Everything else has only got 1 hydrogen. It's got 2. Notice that I've got 2 reactions drawn for it. One reaction, only 1 hydrogen comes off, and we're left with hydrogen sulfate. The second reaction, that hydrogen sulfate then loses its hydrogen, so we go down to just plain old sulfate. Notice the first reaction, the arrow goes one way. That means the ionization happened completely. The second reaction, the arrow went both ways, and the bottom arrow is drawn bigger than the top arrow. That means that second reaction does not happen completely. In fact, because the arrow pointing backwards is bigger, it's not going to happen a whole lot at all. It's going to mostly stay over here as the hydrogen sulfate. So we'll talk more about that when we get to acids and bases, about why that is. Yes?
This is unrelated, but are you going to take these back, or do we keep these?
No, you can keep them as long as you're not like sharing them around.
All right.
Yeah. Yes.
So because you have 1 or greater hydrogen ions released, is it extremely acidic, or?
Yes, it is, because it's going to produce more hydrogen ions. It is going to be producing, a lower pH, but we'll get to pH stuff in chapter 17, 16. Yeah, we got a while before we talk about pH. Yep. All right. So back to the idea of electrolytes. So those weak electrolytes are ones that only ionize partially. What kinds of things are weak electrolytes? Well, weak acids are weak electrolytes. So here is a weak acid, H, so the hydrogen in front tells us it's an acid, followed by C2H3O2. That is a polyatomic ion. Anybody know what the polyatomic ion that is? C2H3O2. No, you don't have to have memorized it. I've got a table. Yeah. This is acetate. C2H3O2 is acetate. So if that is acetate, what is we call the acid based on acetate? Back to chapter 2. If it ends in 8, what do you change the ending to make it an acid? Ic or us? Ic. So if you take acetate, change the ending to ic, what do we have? Acetic acid. So this is acetic acid. Good. Acetic acid. So acetic acid, or the acid base of the acetate ion, is a weak acid. How do we know? Well, it's not one of the 7 strong acids. Also, our ionization here is shown with the arrows going both way, with the arrow that points backwards being the bigger arrow, so it's only going to dissociate or ionize to a small degree. So at the end of the day, in that solution, it's going to be mostly still the acetic acid, not the hydrogen ions and acetate ions. So this makes it a weak electrolyte, which means in solution it produces some ions, but it's still predominantly the molecule, not the ions in solution. The other thing that is a weak electrolyte are going to be those molecular bases that we saw earlier. So here's ammonia again. Ammonia plus water makes ammonium and hydroxide. Again, the arrows point both ways, the bottom arrow usually being written larger because the reverse reaction is dominating. So you end up at the end of the day mostly with the molecules, not the ions. So, yes?
Doesn't that just happen because things don't like to change their charge?
Well, they're already charged, really. They don't want to break apart unless breaking apart is more preferred as far as the reaction rates, but it's not going to be. It depends on how closely that hydrogen is held. In strong acids, the hydrogen is held very weakly, so you put it in water and it's happy to leave. Whereas in weak acids, it's going to hold on to its hydrogen ion more strongly. It's going to take more energy to pull it off.
So at a higher, like if it was heated, the aqueous solution, would there be more hydrogen ions being dissociated?
Depends on whether or not the reaction is endothermic or exothermic, and that's getting into chapter 5. That'll cause whether or not the reaction will go forward or backwards. Actually, that's even getting a little bit into chapter 15. So what about these electrolytes? So electrolytes, we said, can conduct electricity. Well, what about just pure water? Can pure water conduct electricity? No. Pure water, pure H2O cannot conduct electricity. How do we know? Well, here is an image right here. Here we've got a light bulb, so I'm not going all over it. Here we have a light bulb in a solution. Well, this isn't a solution, it's just pure H2O. So all we have is little H2O molecules. The light bulb is hooked up to an electric source, but the 2 electrodes are separated by whatever is in the beaker, the liquid there. In this case, no electricity is going to be able to run through it because it's nothing but H2O. Pure water does not conduct electricity. So why is it dangerous to go swimming during a lightning storm if water can't conduct electricity? Good. The impurities in the water can conduct electricity. So when I said swimming, I didn't specify where you're swimming. What kind of places do we swim?
Pure distilled water.
Pure distilled water. That's a lot of pure distilled water to swim in. More likely, you're going to be swimming in where? Give me an example.
A swimming pool.
Swimming pool. Okay, so swimming pools are not pure distilled water. What do we intentionally add to swimming pools? Chlorine, right, to keep it from growing green algae and bacteria that are going to go into our ears and make us sick, right? So that chlorine, when we put it in, is going to make lots of chloride ions, which are going to be electrolytes and conduct electricity. What about if I'm swimming out in the ocean?
Salt water.
Salt water, right? That's what it means, salt water. There's salt in that water. Salt is an electrolyte, so that is why it can conduct electricity. But water itself cannot conduct electricity. All right, so here I've got a weak electrolyte, which means in solution it's mostly still the molecular form, but a few ions did form. In this case, notice the light bulb did light up, but it's not very bright. So some electricity is conducting through the solution, but not a whole lot. Over here I have a strong electrolyte, meaning majority, if not all, of my compound broke apart to ions. Now the light bulb lights up nice and bright. So that's an example of what strong electrolytes versus weak electrolytes versus non-electrolytes. By the way, if I had taken this water solution and I dissolved something in it that was a non-electrolyte, such as that sugar, sucrose, it would still not light up. Nothing would happen. That was the original lab that you were originally going to do this week, is with little light bulbs, see if they light up in different solutions. But we'll have to do that next week. All right, so let's get to do this nice little flow chart to help you determine whether or not things are going to be strong electrolytes or weak electrolytes. So this flow chart is on page 133 at the top. So the way flow charts work, you start at the top, you answer each question, and that determines which path you take as you move your way down. Do not jump to ahead. If you jump ahead, you can get the wrong answer. Always start at the top, no matter what I give you. Start at the top, work your way down when you're answering these. So let's do first example, methanol. Methanol, let's give the formula for methanol. Methanol is CH3OH. Let's determine what kind of electrolyte is it, a strong, weak, or non-electrolyte. First question at the top of the flow chart. Is the compound ionic or molecular? Methanol. Which way do we go? Ionic or molecular?
That's molecular.
That's pretty molecular, right? What's the dead giveaway if it's ionic? It would start with what? A metal or?
One of those.
There's only one. There's only one that's a positive that doesn't. Ammonium, NH4. Ammonium was the one exception back in Chapter 2 that's ionic but does not contain a metal. All right, so that's pretty darn molecular. So they're going to go ahead and go forward here to the next question. Next question, is this an acid, base, or neither? Why? Okay, so this is a common trick here. A molecular base is one that produces hydroxide ions in solution by taking a hydrogen away from the water. So it turns the water into hydroxide. Molecular bases do not contain hydroxide. They turn water into hydroxide. So this is actually not a base. What did I tell you was the giveaway that something was a molecular base? It ended with a what group? Molecular bases ended with a what group? NH group, right? An amine group, NH something. Does this end with NH something? No. This is not a base, actually. Is it an acid? Nope, doesn't start with hydrogen. So if it's neither an acid nor a base, where are we going to go? Over here to neither. And hey, we've reached the end of the road. The compound is a non-electrolyte. So methanol is a non-electrolyte. Next one, sodium hydroxide. Sodium hydroxide. First question, ionic or molecular? Ionic. So therefore it is a what? Strong electrolyte. Okay, that one was too easy. That one was a letdown. Next one, ethylamine. C2H5NH2. First question, ionic or molecular? Definitely molecular. Okay, so we're going down here. Molecular. Next row, acid, base, or neither? Base. Why? Good. It has an amine and NH group, so it's a base. Therefore, it is a what? Weak electrolyte. We liking this flow chart? Well. Ready for the last one? Okay. All right. Hydrofluoric acid, HF. Ionic or molecular? Molecular. There's no metal. There's no ammonium. It's molecular. Okay, going down here. Next row, acid, base, or neither? Acid. Good. It's got hydrogen in front, plus the name is hydrofluoric acid. There's a hint. So down to the next row. Is it one of the 7 strong acids listed on table 4.1? Hydrofluoric. No, it is not. Hydrochloric, hydrobromic, hydroiodic, but hydrofluoric is not one of the 7. Therefore, it is what? Weak electrolyte. Ta-da! Molecular compounds are all nonmetals. Ionic compounds start with either a metal or they start with NH4 ammonium, the polyatomic cation. Ammonium NH4 is the only polyatomic cation that neither contains metals but still forms compounds. Back from chapter 2. How we feel about section 4.1? Like, you said chapter 4 was hard. We're good, right? This is why you guys lose trust in me. It was easy. All right. Going on to section 2, precipitation reactions. All right. So first of all, where do we hear the word precipitation thrown around? The weather, right? What does precipitation mean? Rain or snow, or we're in North Carolina, ice, right? Freezing rain. It freezes halfway down, or it freezes the moment it hits the power lines and brings the power lines down, right? Fun times. Or it freezes the moment it hits the road. So precipitate, when we use that in terms of weather, we are talking about water, H2O, leaving the clouds, leaving the air, and coming down. So it is up in the clouds, which is mixed with air, the atmosphere. That is a solution. It's not aqueous solution, what we're talking about here, but it is still a solution up there. The air we're breathing right now, atmosphere, is a solution. What's the primary component of the air we're breathing right now? Nitrogen, right? We're in a nitrogen-rich atmosphere. So water is up there in the clouds. It is technically dissolved in the solution of nitrogen, oxygen, all the other gases we have in our atmosphere. When it becomes rain, snow, ice, whatever, and falls down, it is being released from the solution. So precipitation is when something is being released from the solution. In terms of an aqueous solution, the precipitation we're going to be talking about is when a solid is released from the aqueous solution. So precipitation is when a solid is going to be released. Sure do. So let's look at an example here. Here we have, I've got these compounds. Let me pull them out. More exciting than a picture, right? I think I got the reactions, the ratios off. There we go. All right, so it turned yellow. We've dealt with labs in the past where we have seen things change color. In fact, turning yellow was the point of the second lab we did, that we added bromothionyl blue to acids and bases and solvent and bases. It turned blue, whereas in the acids it turned yellow. So here it turned yellow, but not just yellow, it also turned cloudy. So that cloudiness is a hint that more than just a color change is going on. So by cloudy, I mean you can no longer see through it. If you can no longer see through it, that must mean there's some particles suspended in that solution that are blocking you from being able to see through it. And if you leave it sitting for a while, those particles will settle down to the bottom. So I'm going to pass this around. Don't drink it, but it's not like toxic or anything. You can look closely at it and see that not only did it change color, but actually it created a solid precipitant. That solid precipitant that formed out of the solution then was, in this case, the lead and the iodide formed a complex that was insoluble, so it came out of solution. So this is a precipitation reaction. Two things that were soluble mixed together. One of the products was insoluble, so it came out of the solution. If you leave that sitting a while, that solid will just settle down to the bottom, or you could put it in a centrifuge and spin it and get it to go down to the bottom so you can separate it out. So I use that word soluble, things that are soluble versus insoluble. So Things dissolve in water through a process called hydration. When hydration doesn't work, then it is insoluble. Hydration is the process by which H2O molecules surround something and dissolve them. So a simple version of this is just some sort of ionic compound here. Water. We'll talk more about water being polar way in Chapter 9, but for now, these little squiggly lines all around the H2O molecules are partial charges. We already learned in Chapter 2 that ionic compounds have positive and negative charges. Positive ions, cations, negative ions, anions. H2O molecules are going to have a negative end and a positive end, which allows them to kind of mimic ionic compounds. So the positive ends of the water molecules are going to attract the negative ions, while the negative end of the water molecule is going to attract the positive ions, and it's going to pull them apart and surround them. So this is hydration, how the water is going to dissolve things. Solubility refers to when something is able to dissolve, and to some degree. Just because it can dissolve doesn't mean it's going to have an infinite amount that can dissolve. If I take salt and I sprinkle it in water and stir it, it'll dissolve, sure. But if I have a cup of water and I dump a quarter of a cup of salt in it and stir it, is all that salt going to dissolve? No. There's a maximum. There's a limit, right? There's a limit to how much can dissolve, and then it won't dissolve anymore. That's called its solubility, the maximum amount of solute that can dissolve in any given amount of solvent at a specific temperature. For most compounds, if we change the temperature, we're going to change the solubility. Not sodium chloride, but for other things. For example, sugar. Sugar, we know, same idea as salt. If you dump a cup of sugar in a cup of water, it's not all going to dissolve. But what if you really need all that sugar to dissolve? You're making sweet tea, and you really want it all to dissolve. What could you do? Heat it up. Heat up the water, right? So that's how we make sweet tea. It's not by your server bringing you unsweetened iced tea and giving you some sugar packets. That never works, right? You can never get it to dissolve enough sugar because the iced tea is cold and it doesn't want to dissolve that much sugar. That's why they ruined it. I laugh because actually, even though I grew up in the South, I was raised by a Northerner and I don't like sweet tea. But my husband was raised in the South and is a Southerner and loves sweet tea, so he makes fun of me. But when we go to the occasional restaurant that clearly was not made by a Southerner and they bring out him an unsweetened tea and he takes a sip of it unprepared, the look on his face is priceless. Yes. And that's why he won't let me take him to an Asian fusion restaurant anymore. All right, so solubility. How do you tell what kind of things are soluble and insoluble? We're going to have some rules here. We're on page 135 of your textbook. Down at the bottom are some rules for determining what kinds of compounds, we're talking about ionic compounds, are going to be soluble versus insoluble. Thank you. So the first rule up here is that compounds containing, let me get my little laser pointer, compounds containing an alkali metals again are the first family, so that's our lithium, sodium, potassium, rubidium, cesium, or the ammonium ion, that NH4, are listed as water soluble, and there are 0 exceptions to this. Second rule says if you contain nitrate, acetate, chlorate, you are soluble. Once again, there are no exceptions. Third rule, if you contain chloride, bromide, iodide, you are soluble, but now we have exceptions. If you have silver, mercury, or lead, then you are insoluble, and that's exactly what we formed here. Here, we took iodide and reacted with something that contained lead. So once the iodide and the lead made a compound, that was one of the exceptions, it became insoluble. Now, common misconception in this table is that if it has any of the insoluble exceptions, it is automatically insoluble. These are exceptions to this rule. This is lead nitrate. It is soluble. You don't see lead ions floating around in there because it completely dissolved, because it has nitrate. Nitrate is soluble with no exceptions, so putting lead in there did not make it insoluble. Whereas the iodide with lead did. So these exceptions only apply to this rule. You have to have the two of them line up. Simply having Lead does not mean it's insoluble. It's only lead when you're one of these rules. Last rule, sulfate is soluble. It's got even more insoluble exceptions. All right. We do have a second table on the next page, page 135 or 136. Has a table. Now this table switches the game. Now the rule column are things that are insoluble, and then the second column are exceptions that are soluble. But these exceptions that are soluble just restated the first rule from the last page. Lithium, sodium, potassium, rubidium, cesium, and ammonium would be soluble. That's just restating this rule here. So honestly, you can get away with just the one table if you play along with this idea. If there's no rule saying that it's soluble, what should we assume? It's insoluble. Yeah. If you use that idea, you can technically get away with just the first table. If there's no rule saying it's soluble, we're just going to assume it's insoluble. I mean, we can just use the first table and be fine. So let's try this out. A couple of compounds. First one, silver nitrate, AgNO3. Soluble or insoluble? Soluble, why? Good, it contains nitrate. Because it has nitrate, it is soluble. There are no exceptions to that rule, so that's definitely soluble. Soluble because it contains nitrate. Next one, calcium sulfate. Insoluble. Why? It has sulfate. Sulfate is soluble.
Also contains CHM.
Good. Also contains calcium, which makes it one of the insoluble exceptions. So that makes this insoluble. Why did I do that? It tasks me. Whew, insoluble. Yeah, I love how it erases random letters in the middle, not the last ones I wrote. Any questions about why the first one's soluble and the second one is insoluble? Next one is potassium carbonate, K2CO3. Soluble or insoluble? Soluble. Good. Why? Good. It's got potassium. Potassium is soluble, no exceptions. Soluble. So you just need to match one rule. Once you've matched one rule, if there's no exceptions, you're done. You didn't need a rule for carbonate. You didn't need to go over this page and went, oh, okay, carbonate's insoluble, but then potassium soluble. You could have just used the first table and went, oh, wait, potassium soluble, no exception, I'm done. So how do we feel about this? Good? All right. And there are these examples we just did. All right. So now we're going to start learning how to write our own equations. So in Chapter 3, we dealt with balancing chemical equations, but I went ahead and told you what the reactants and products were. Now I'm just going to tell you the reactants, and it's going to be up to you to find the products. So a molecular equation shows you the reactants and the products as compounds, and then we're going to talk about ionic equations and net ionic in a bit. But I wanted to show you a quick what kind of reaction this is, because I think that will help you better determine what the products are. So I'm going to open a new slide. Sure, keep them. And talk about this idea of double replacement, sometimes also called double displacement. Double replacement. So I have some compounds, AB plus CD. Now, why did I do them in different colors? I did them in different colors because these are representing ionic compounds. Ionic compounds, which is always written first, the positive or the negative ion? Positive, good. Cation's always written first. So in this case, I've got the blue ones are going to be my cations. The green ones are going to be my anions. Can you put two cations together? No, why not? Same charge repels, right? So I cannot put A and C together. They're both positively charged. They won't like it. But double replacement, what do you think I'm going to do? Good. I'm going to switch partners, okay? This is a square dance. Do-si-do. Switch for partners. Here we go. So A here, A is going to give up on B and go with who? D. C is going to give up on D and go with who? B. And that is how you figure out what your products are going to be. Yeah. So this is like the one thing I guess students always, Chapter 4, they always say this is the most hardest thing. I don't know how to figure out what the products are. That is all it is. And then a little bit of Chapter 2, being able to go from names to formulas and, you know, balancing ionic charges. But that's all there is to determine what the products are. You switch partners. So let's do this with words first. I think words will be less confusing, and then we'll look at the chemical formulas. So let's just do it with the ones that we did here in class. So I have lead nitrate. I'm just going to switch just to black so we don't confuse ourselves. Lead nitrate plus, and then this one was potassium iodide. All right, so if those are my two reactants, can you determine what the products will be? Just names. I'm fine with names right now. Lead iodide and potassium nitrate. Room nitrate. There. Is that bad? That's terrible. Now let's see what we remember from Chapter 2 and write the formulas of these things. All right. This is a transition metal, so I technically should have had Roman numerals in here. This is lead 2. Bad me. Okay, lead 2. Lead 2 nitrate. What is the formula for lead 2 nitrate? Pb. Here's our lead. What's the formula for nitrate? NO3 is nitrate. How many of those am I going to have? 2. Parentheses 2.
Do you need to put the charge on lead?
No. Once you make a compound, the charge is on. Does anybody not see why I needed 2 nitrates? Remember from Chapter 2 and the test you just took? Why there should be 2? Okay. Yep. Yep, that's -1, but the lead was 2. So that's why I need 2. State of matter. Lead nitrate. To figure out states of matter, we go to the solubility table. So lead nitrate, according to the solubility table, there's a solubility table. Would that be soluble or insoluble? Lead nitrate. Soluble because there's nitrate. No exception. So if it's soluble, what state of matter will it be? Good, aqueous. There we go. Potassium iodide. What's the formula of potassium iodide? K is potassium. I, what ratio do they go together in? What's the charge on a K? +1. What's the charge on an I? -1. So they go together in a what ratio? 1 to 1. Because potassium is +1, iodide is -1, 1 to 1. Okay. Next question, soluble or insoluble? Soluble. Potassium's soluble, no exceptions. So that's aqueous. So there's our 2 reactants. Now products. Lead 2 iodide. So here's our lead, here's our iodide. What ratio will those need? PB. I2, good, because lead has 2 plus, whereas iodide is only 1 minus, so I'm going to take 2 of these. Lead iodide, soluble or insoluble? To our table if we're not sure. Insoluble. We've got iodide, but lead was one of the exceptions, so that becomes insoluble. If it becomes insoluble, what state of matter does it become? Solid, good. Last one, potassium nitrate. Potassium and nitrate, what ratio will those go together in? 1 to 1. Good. Potassium is 1 plus, nitrate's 1 minus, 1 plus, or 1 to 1. What state of matter is that going to be in? Aqueous. Potassium's one of the rules, first rules, soluble no matter what, so that's aqueous. All right, so here's our chemical equation. What looks wrong about it? It's not balanced. Okay, it's not balanced. Okay, we can fix this. We can fix this. Okay. What's not balanced? Iodines aren't balanced. Okay, how can we fix that? 2 in front of Ki. So now iodides are balanced. What's still not balanced? Now potassium and nitrates aren't balanced. So how can we fix that? 2 in front of potassium nitrates. Now I have, switch laser pointers, I'm not drawing all over it. 1 lead, 1 lead. 2 nitrate ions, 2 nitrate ions. 2 potassiums, 2 potassiums. 2 iodides, 2 iodides. Am I balanced? Yes. Okay, that wasn't so bad to balance, right? Compared to some of the ones in Chapter 3, that wasn't bad at all. This is our molecular equation. So as far as what you guys would be expected to do, I would tell you mix lead nitrate and potassium iodide and then write this equation. So it would be up to you to go from the name to the formulas, Chapter 2. Dose-y-dose, switch partners, figure out what your products are, and write those formulas, and then balance them. And that's all there is to writing the molecular equation for a precipitation reaction. Now, there is not always a precipitant. Yes, there was this case, we had a solid, but as you'll see on tomorrow's lab, just because you mix 2 things together does not always mean a solid forms. So, in this case, there was a precipitant. I heard that from a student saying their tutor told them there has to be a precipitant, so if both of them show up aqueous, just make one of them solid. I'm not quite sure if that's true or not, in which case that tutor needs to get schooled. No, there's not always a precipitant. So here's our molecular equation. So if this is a molecular equation, I keep on saying that word molecular, doesn't seem to fit this. Why was the term molecular equation does not seem to fit with this kind of equation? Those are ionic compounds. They're not molecules, right? Ionic compounds in water tend to do what? Dissociate. They break apart. So while this is the molecular equation, it is not really what actually is in solution. What actually is in solution is, if it dissociated, the ions. So the next thing we're going to have is something called an Ionic equation, where we show the actual ions that are in solution. And we're going to take each of these and break them apart. So let's start that. Switch colors. All right. First of all, lead nitrate. Now we're going to have lead ions and nitrate ions. So lead ions. What's the charge in a lead ion? 2 positive. Now, it is in water, so it is also aqueous. So it's still going to be aqueous. All right. Next, we have nitrate ions. What's the formula for a nitrate ion? NO3 with 1 negative. We'll just put a negative there. Also aqueous. Now, how many nitrate ions do we have floating around here?
We're supposed to have 2, but we have 1 now.
We have 2. So how do we show there's 2 nitrate ions floating around here? Putting a 2 where? In front here. All right. So when we break apart ions, here, this is going to become my stoichiometric coefficient. Everybody see that? That one's kind of tricky. Let me try this. I like these better because this lets me move the stuff around. So when you break apart the ionic compounds and you get your individual ions, then you list it like it's stoichiometry. So how many of each ion you have becomes the coefficient, not the subscript. Subscripts tell you how many is in a compound. Once you break apart, you're no longer a compound. No, I don't want to cover anything. I think visualizing is a little bit better once this loads. Okay. All right. Let's do this. Okay, so here's our compound. We have lead, and then we have a nitrate over here, and we have a nitrate over here. And our lead has a 2+ on it. So there's our happy compound. When we dissociate, these things are going to break apart in solution. So this thing here, come on, is going to float away. Wow, yeah. They floated away. Okay, now if I describe what I have here, I would say now the charges don't cancel anymore. So now I can't say I have lead nitrate. Now I have lead ion, which is 2+, and I have 2 nitrates. So that's why that 2 became a coefficient, no longer a subscript. We broke it apart. Now these two things are floating separate from each other. They're not still stuck together. Commonly I see people want to put nitrate with a 2. That means I made a compound between 2 nitrates. Why would that never happen? They're the same charge. They repel. These two things are trying to get as far away from each other as possible because they're both negatively charged. So that is wrong. Once it is no longer a compound with the positive ion, you no longer should have those subscripts on the outside of an ion. Now this subscript is still there because that's part of the ion. That's fine. But subscripts showing you how many ions you have, those become coefficients. Does that make more sense now? Okay. So next, our potassium iodide. So we get potassium ions. How many of those do we have in this balanced equation? 2. So we write 2 potassium ions. Everything gets a state of matter. Now iodide ions, how many of those do I have in this balanced equation? 2. Good. This 2 gets distributed to both of them. So I have 2 potassiums and 2 iodides. That's what that means. Carry everything down correctly, you should still be balanced and not need to rebalance. If you needed to rebalance, that means something didn't get carried down correctly. Next thing I have up here, lead iodide. Is lead iodide going to dissociate? No, why not?
Because it's a solid.
It's a solid. It's not even in the solution. It didn't even dissolve. You cannot dissociate unless you at least are dissolved. You're just sitting there as a solid. You're not going to break apart into ions. So I'm just going to carry that down as it is. I'm not going to change a thing. It did not dissociate. It's still a solid. Lastly, the potassium nitrate. Is that going to dissociate? Yep. And just like with the potassium iodide, I'm going to distribute that too. So I'm going to get 2 potassiums and 2 nitrates. And everything gets a state of matter. So here's the fun part, entering that whole thing into Connect. You guys don't look excited about that. Make sure everything has a state of matter. Charges are always up in the superscript. Subscripts are in the subscript. So here is our molecular equation versus our ionic equation. The last thing we have is something called a net ionic equation. So let's look at this like a math equation, and this arrow is our equal sign. What happens in algebra when you have the exact same things on both sides of your equal sign? What do? They cancel out, right? Do I have anything that's exactly the same on both reactant and product side? Exactly the same. Potassium ions. Highlight them here. I've got potassium ions on both sides that are exactly the same. That meant at the start of the reaction, I have potassium ions floating around. At the end of the reaction, I have potassium ions floating around. So what did potassium do in this reaction? Nothing. Not a thing. That is what we call a spectator, somebody who just sits there and watches instead of doing anything. We have some of those in labs sometimes, right? Spectator ions are things that did nothing in the reaction. You can tell them because they are the same before and after and did not change at all. In our net ionic equation, we're going to ignore them because they didn't do anything. They were just spectators. So we're going to cancel that out. Anything else here that is a spectator ion that did nothing? Nitrate. Yes, nitrate did nothing. And it's on both sides exactly the same. Hey, go back. Exactly the same on both sides. Whew. No, that was a different example. I did a different example here. So what is left over is going to be our lead ion, aqueous. Our iodide ion, also aqueous. And then on the product side, the only thing left is that solid lead iodide, PbI2. I, solid. This is called our net ionic equation. It's what actually reacted, if anything. Now, if we didn't have a precipitant in this example, everything was aqueous, everything was an ionic, everything would cancel. And for our net ionic equation, we would just write no reaction. Nothing happened. Sometimes you mix things together and nothing happens. We'll see tomorrow. Sometimes nothing happened. I did give Dr. Bradshaw the answer key so he knows what's supposed to happen. So if you're like, I don't know if something happened or not, just ask him. All right, any questions about molecular ionic and net ionic? We still got a couple minutes. Still got 6 minutes with you guys. Okay. So here's an example of an ionic equation. Let's look at this ionic equation and turn it into a net ionic equation. So this ionic equation, I've got sodium ions plus sulfate ions plus barium ions plus hydroxide ions yields sodium ions plus hydroxide ions plus barium sulfate solid. So in this equation, what is a spectator ion? Sodiums and hydroxides. So if I wrote the net ionic equation, it would just be sulfate plus barium makes barium sulfate solid, would be your net ionic equation. That's you.